Welcome back to class. So we're going back in time today. We're going to go back to Athens in 1896 and visit the first modern Olympic Games. So the Olympic Games had not been done since classical times until 1896, when the first modern Games were held in Athens. And the Games were held in this stadium, which is the Pan-Athenaic Stadium. It was built in 329 BC, and it was built entirely from marble. It originally had a seating capacity of 50,000, but for the Games in 1896, the stadium held 80,000 people. There were 14 nations participating, 241 athletes in 9 sports. As we know, these Games have become an immense success. People look forward to the Olympic Games every few years. The Games went more or less without a hitch, although the historical records that are available suggest that it snowed during the Games in April, the 6th and 7th, just outside of Athens, an event that is increasingly unusual in today's world. There was another event in 1896 of great note that was happening at the same time as these Olympic Games. It was not an Olympic sport, or any sport in fact. It was a scientific publication. It was a publication by Svante Arrhenius, who's a Nobel Prize-winning chemist. And in that same month of April 1896, as the Olympic Games were unfolding in Athens, his paper, published in the London, Edinburgh, and Dublin Philosophical Magazine and Journal of Science, was the first to describe the ability of greenhouse gases to trap heat in Earth's atmosphere and make the suggestion that if coal would be burned over time, that if it continued to be burned over time, the planet's climate would warm. So this is 1896. In this paper, Arrhenius refers to a prior paper written by the French scientist Fourier. And in Fourier's paper, which appeared in 1824, he describes the greenhouse effect, that the Earth's atmosphere, the gases in Earth's atmosphere, are able to trap energy emitted towards Earth from the sun. So the idea of the greenhouse effect, the fact that gases trap heat within Earth's atmosphere, goes back into the early 19th century. So the idea that gases trap heat and that adding greenhouse gases, such as carbon dioxide being the most important of them, might affect the planet's climate, are ideas that go back to the 19th century. They're really nothing new. How does the greenhouse effect work? As Fourier described it, he said that the atmosphere acts like the glass of a hothouse because it lets through the light rays of the sun, but retains the dark rays from the ground. What is he talking about, light rays and dark rays? So here's an illustration of the greenhouse effect. And what it shows is that energy that comes from the sun comes towards Earth's atmosphere. Some of that incoming, what's called here solar radiation, its energy, goes through the atmosphere and heads towards the Earth's surface. Some of it, however, is reflected back towards the atmosphere. What does come through the surface, some of it is absorbed on land and in the oceans, and some of it's reflected back from the ground towards the atmosphere. And what's interesting is that as the sun's radiation comes through the atmosphere and hits Earth's surface and is reflected back, that radiation changes. It changes in its wavelength. And the wavelength of radiation is simply the distance between the waves in the radiation that's emitted. For those who aren't physicists in the audience, suffice to say, wavelength is a property of radiation. All radiation, including the light that's making it possible to see me, as well as ultraviolet radiation from the sun or infrared radiation that comes off the Earth's surface, all is determined, has a physical property that is its wavelength. For those who are physicists watching this, I hope you're not cringing too much, but it is an important feature of radiation that there is a wavelength, and that wavelength changes as energy passes through the Earth's atmosphere and is reflected off the Earth. So Fourier was describing the change in the energy. The light rays come through, but the dark rays that reflect off the Earth are trapped by these greenhouse gases. So what's important about that change in wavelength is that it matters to the ability of greenhouse gases to trap heat. So what this illustration shows is the distribution of the wavelengths of radiation coming from the sun. So downgoing solar radiation has wavelengths in the ultraviolet and visible range, mostly. That's why sunlight makes it possible to see us. But radiation that's coming up from the Earth, the upgoing thermal radiation, is largely in the infrared spectrum. So why does that matter? Well, it matters because if you look at where gases, like carbon dioxide in particular, absorb radiation, it overlaps with the outgoing radiation from Earth. So that this radiation is not absorbed, you'll see here in carbon dioxide that there's no absorption in these wavelengths. But as that radiation comes down towards Earth, gets reflected and changes, there's then the ability of the radiation to be absorbed. And this is a critical point because people would ask, how is it that the same radiation that, in principle comes from the sun down towards Earth and gets reflected can somehow pass, a large part of it pass through the atmosphere, come off Earth's atmosphere, and then get trapped as it comes back? And that's because the energy actually changes as it gets bounced off. And that change in the energy makes it possible for gases like carbon dioxide to absorb the energy coming back out. So for some people, the idea of wavelengths changing and energy changing is somewhat abstract. So I wanted to give an illustration that might make it come closer to home. So it turns out that it's not just the Earth's surface that gives off infrared radiation. We, in fact, do as well. If you had a special camera that didn't absorb radiation in the visible spectrum, but instead in the infrared spectrum of radiation, and you took a picture of a human being with such an infrared camera, you would see a picture that looked like this. And you'll see that where there's heat on the body, individuals light up. So our hands and our faces, and you'll see that this person's glasses are cooler. This is actually a match that the person has lit. But I only show this to you to show that infrared is visible, just not to our eyes. It is visible to specialized cameras. The next question that one might have is, greenhouse gases, it turns out, are a very small percentage of Earth's atmosphere. And how is it possible that such gases in such small concentrations can affect the temperature of the planet? So just to put it in perspective, 78% of the Earth's atmosphere is nitrogen, 21% is oxygen, about 1% is argon, leaving less than 1/10 of 1% for all the other gases that go into Earth's atmosphere, and there are many. Of that 1%, most of it is carbon dioxide. But carbon dioxide as a whole constitutes about 0.039% of the gases in Earth's atmosphere. So you would say, if carbon dioxide is in such a small concentration, how can it possibly affect the planet's climate? Well, the answer is that things in small concentrations can have enormous effects upon the planet. One illustration of that is that ozone in Earth's atmosphere is at a concentration of 0.000007. I think I got enough zeros in there. But it is a fraction of the concentration of carbon dioxide. And yet, the ozone hole, which is a depletion of ozone in the Earth's atmosphere, which is largely over the Antarctic, as is pictured here, is a major problem for ultraviolet radiation coming from the sun getting through the Earth's atmosphere. The ozone layer protects us. It shields us from ultraviolet radiation that can damage DNA and is associated with skin cancer. So here's a gas in the atmosphere, ozone, that is a fraction of the concentration of carbon dioxide, and yet at that concentration it has extremely important effects at protecting us from DNA damage from radiation. The other side of it is that if you took all of the greenhouse gases out of Earth's atmosphere, what would it do to the planet's climate? It would be about 60 degrees Fahrenheit or 28 degrees Celsius cooler. So greenhouse gases are essential to maintaining the planet's temperature as it is. So that very, very small amount of carbon dioxide has an enormous effect upon the overall temperature of the planet. The atmosphere is essential to maintaining the planet's climate. So clearly greenhouse gases matter to the temperature on Earth, but that leads us to our next question, which is how do the concentrations of greenhouse gases in the atmosphere today compare to those of the past? And to get at that question, we have several pathways. We can look at ice cores, as we did for temperature. And if you looked really closely at the last picture of an ice core, you would have seen little black dots. And a closer inspection of those would show you that those little black dots are in fact air bubbles that are trapped in the gas. And just as with the water that can be used to understand the temperature going back in time, you can drill down deeper and look at bubbles trapped in that ice as little time capsules of the Earth's atmosphere going back hundreds of thousands of years. This is a graph of data from one of the ice cores in Vostok, Antarctica, that goes back hundreds of thousands of years. That's pictured in yellow. There's also a temperature record which goes back several 100,000 years. And what you'll see is that the carbon dioxide concentration of Earth over the past several 100,000 years has gone up and down, but it's generally gone between about 200 parts per million and about 300 parts per million in the last several 100,000 years until the 20th century. And you'll see at the very, very end of this graph a little green line. And that green line represents carbon dioxide concentrations that have been measured at a volcano in Hawaii called Mauna Loa. And during the last several decades, between 1958 and 2003, there's been a tremendous increase in atmospheric carbon dioxide. So that today we're at 396 parts per million, very small concentration. But a much higher concentration than has been present in the Earth's atmosphere at any point in the last 600,000 years. Now some of you may question the ability of us to compare the concentration at Mauna Loa, a volcano, with those in the Antarctic ice core, and we have several lines of evidence that show that in fact concentrations of greenhouse gases have been below 300 parts per million for hundreds of thousands of years, and that since the Industrial Revolution they've gone higher, and that's what I'm going to turn to in this figure. So this is a graph that shows recording of carbon dioxide in various places over time. The red dot in the graph represents Mauna Loa, that mountain in Hawaii. That's this guy here. And the blue is the South Pole. And over time you can see more and more carbon dioxide stations appearing. And this is the concentration in parts per million of carbon dioxide. What this graph shows you is the Earth breathing in and out. So every year as plants grow, they sequester carbon dioxide from the atmosphere, and then as they die, they release it. So in the spring, the concentration falls. In the winter, it increases. And it turns out that most of the vegetation on Earth is actually in the northern hemisphere. So you actually do get a signal of the Earth breathing in and out. The northern hemisphere cycles of nature overwhelm the southern hemisphere. So what you will see is that over time we have all of these carbon dioxide records showing that the concentrations of carbon dioxide have gone up from the late 70s at about 330 parts per million to today, this is 2011, 391 parts per million. But let's take a look going further back. So that's when we rely more upon ice cores. And as this graph extends backward, we have the data from Mauna Loa, which is here in green, going back to 1958. And then we'll add to it data from several ice cores from around the world. And you'll see that the concentration here is centered largely around 280, going back now to 500, and then to the year 0. And then we can go back, as we've done, even further. And what's nice here on the left is you'll see the summary. So in 2011, it was 391 parts per million. 1979, 336 parts per million. The pre-industrial concentration, so before the Industrial Revolution, would have been about 278 parts per million. And then in the Ice Ages, the average was around 185 parts per million. So we have multiple data points showing us that carbon dioxide concentrations, going back hundreds of thousands of years, have always been below certainly 300 parts per million, going back hundreds of thousands of years. And today, we're up here at 396 parts per million. Now, carbon dioxide is one greenhouse gas, but there are others. They include nitrous oxide and methane, and these graphs show in a very similar way to carbon dioxide that over the last 10,000 years, the concentrations of methane and nitrous oxide have gone up dramatically as well. So, we now have shown that the temperature on Earth has been going up on average. We have shown that there have been responses in the physical and living world to those changes. We have gone through the fact that scientists have understood the importance of greenhouse gases to maintaining the Earth's temperature and potentially contributing to increased warming as concentrations rise. And we've shown that there have been dramatic increases in greenhouse gases over time, and in particular since the start of the Industrial Revolution, as fossil fuels have been burned. The burning of fossil fuels are the major source of greenhouse gas emissions. So this all leads us to the question of what evidence do we have that these greenhouse gases are in fact causing the rise in temperatures that we're seeing? And that's the question that we're going to tackle next time. See you then.